Today we're scaling AI infrastructure, the engineering nightmare of building data centers that consume more power than small countries to run trillion-parameter models that might achieve consciousness and immediately crash your Kubernetes cluster. Not the clean cloud-native bullshit from vendor presentations, but the real infrastructure hell where your GPU farm catches fire, your electricity bill exceeds NASA's budget, and you realize you've built the most expensive space heater in human history using nothing but NVIDIA markup and venture capital. 3 engineers, 1 data center that melted, and 45 minutes of pure infrastructure horror. I'm Sam, and someone's definitely getting fired for the power bill.
I've been building AI infrastructure for 5 years. 5 years of explaining to executives why we need 10,000 GPUs to run a chatbot, why our cooling system uses more water than a small city, and why the power company called to ask if we're mining Bitcoin. Last month, our training run crashed because a butterfly landed on a cooling fan in rack 47. The model had learned for 3 weeks. We lost $2 million because of a butterfly. I don't believe in chaos theory anymore, I live it.
My job is making Kubernetes work with AI workloads. You know what's fun? Orchestrating containers that each consume 80 gigabytes of GPU memory and cost $40,000 per node. One pod failure brings down the entire training job. I've seen grown engineers cry when their 8-week training run dies because someone deployed a logging update that used 1% more memory.
I optimized distributed training across thousands of GPUs. Ever tried to debug a deadlock across 2048 A100s? Each GPU is doing slightly different work, communicating with every other GPU, and the failure could be anywhere. It's like trying to conduct an orchestra where every musician is playing a different song and half of them are on fire.
Dr. Kim, you're our guide through this infrastructure apocalypse. Marcus and Luna, prepare to explain why running ChatGPT requires the electrical output of a small nuclear plant, and why your Kubernetes cluster achieved sentience before your AI model did. No mercy, no, it scales horizontally.
Let's start with the fundamentals. What happens when you try to scale from 1 GPU to 1,000 GPUs?
Everything breaks. Your training script that worked perfectly on a single GPU becomes a distributed systems nightmare. Network latency dominates, memory management becomes impossible, and you discover that your beautiful PyTorch code has more race conditions than a NASCAR event.
Why can't you just add more GPUs? More compute should mean faster training.
Communication overhead. In distributed training, GPUs need to synchronize gradients after every batch. With 1,000 GPUs, you're doing all-reduce operations across the entire cluster. Network bandwidth becomes the bottleneck. You spend more time waiting for gradient synchronization than actually computing.
What's the network topology for these GPU clusters?
InfiniBand fat tree networks with 400 GB/s links. Each GPU has dedicated high-speed connections to every other GPU. The networking hardware costs more than most companies' entire IT budgets. We're basically building the internet, but for matrix multiplication.
How much power does this consume?
A single A100 GPU consumes 400 watts. Multiply by 10,000 GPUs, add cooling, networking, storage, you're looking at 20 to 30 megawatts. That's enough to power 15,000 homes. We literally have our own power substation. The electric company built new transmission lines just for us.
What about cooling? How do you dissipate that much heat?
Liquid cooling systems that pump thousands of gallons per minute. Each rack has dedicated cooling loops, temperature sensors, and emergency shutdown systems. We monitor coolant temperature more carefully than mission control monitors rocket launches. A 2-degree temperature spike can crash the entire training job.
What's the failure rate at this scale?
Constant failures. With 10,000 GPUs, statistically something fails every few hours. A memory error, a network glitch, a power fluctuation, any single failure kills the entire distributed training job. We've built the world's most expensive domino setup.
How do you handle fault tolerance?
Checkpointing every few minutes. We save the entire model state 175 billion parameters to distributed storage constantly. When something fails, we roll back to the last checkpoint and lose maybe 10 minutes of training. But saving 700 gigabytes of model weights to disk every few minutes is its own nightmare.
What about storage? How much data are we talking about?
Petabytes training datasets are hundreds of terabytes. Model checkpoints are hundreds of gigabytes each, and we keep thousands of checkpoints. The storage system has more drives than most data centers. We're basically building a digital library of Alexandria, but for teaching machines to predict the next word.
How do you orchestrate this chaos? What does the software stack look like?
Kubernetes on steroids. Custom operators for GPU scheduling, distributed training controllers, automatic failover systems. We wrote more infrastructure code than model code. The YAML files alone are larger than most applications. We're running a small operating system just to manage the infrastructure that runs the actual AI.
What happens when you need to update the infrastructure?
Rolling updates across thousands of nodes while maintaining active training jobs. It's like performing surgery on a patient while they're running a marathon. One misconfigured node can corrupt the entire training run. We've lost weeks of training because someone deployed a kernel update that changed GPU memory allocation by 1%.
How much does this infrastructure cost?
GPU cluster $500 million, networking $50 million, storage $25 million, power and cooling $100 million. That's before you factor in the data center real estate, which costs more than Manhattan office space. We built infrastructure that costs more than most countries' GDP.
What about operational costs?
Electricity $2 million per month, cooling $500,000 per month, maintenance $1 million per month. The operational costs are higher than most companies' entire revenue. We're spending more on electricity than small countries use for their entire population.
How do you monitor this infrastructure?
Thousands of metrics per second. GPU utilization, memory usage, network throughput, temperature, power consumption, training loss, gradient norms. We have more monitoring infrastructure than most companies have actual infrastructure. The monitoring system generates more data than the models we're training.
What's the most catastrophic failure you've experienced?
The great cooling failure of 2024. A software bug in the cooling system caused all pumps to shut down simultaneously. 10,000 GPUs started overheating at once. The emergency shutdown system couldn't handle the power surge. We lost 6 weeks of training and melted $50 million worth of hardware. The smoke was visible from space.
How do you debug issues at this scale?
Distributed debugging hell. The problem could be anywhere: a single GPU, a network switch, a storage node, a cooling system. Log aggregation across 10,000 nodes generates terabytes of data per hour. We built AI systems to debug our AI infrastructure. It's artificial intelligence all the way down.
What about security? How do you protect this infrastructure?
Physical security like Fort Knox, network security like the Pentagon, biometric access controls, air-gapped networks, encrypted everything. We have security guards with security clearances watching security cameras that watch other security cameras. The security budget is larger than most startups' entire funding.
How do you handle capacity planning?
Forecasting the unforeseen. Model sizes double every few months, training requirements grow exponentially, but GPU supply chains take years. We're ordering hardware for models that don't exist yet, using techniques that haven't been invented. It's like trying to build airports for aircraft that might be able to fly.
What's the future of AI infrastructure?
Bigger, more expensive, more complex. Models will hit trillion parameters, clusters will need millions of GPUs, power consumption will rival small countries. We're building the most expensive computational infrastructure in human history, and it's not nearly big enough.
Are we hitting physical limits?
Power density limits, cooling limits, network bandwidth limits. We're approaching the physical constraints of silicon and fiber optics. The next generation of AI infrastructure might require new physics. We're literally bumping against the laws of thermodynamics.
And nobody knows if scaling will keep working. We're betting billions on the assumption that bigger models are better models. If that assumption is wrong, we've built the most expensive mistake in history.
Holy fucking shit. So we've built computational infrastructure that consumes more power than countries, costs more than space programs, and might be fundamentally hitting the limits of physics. But hey, at least our chatbot can write haikus about its existential dread.
Welcome to the age of computational megaprojects. We're building digital pyramids that might collapse under their own complexity, and nobody knows if we're solving the right problems.
This episode brought to you by Engineer Panic, where we document the slow-motion construction of humanity's most expensive computational monuments. Because understanding why your electricity bill exceeds small nations is probably important. We're back, let's talk about the human cost of this infrastructure madness. Marcus, what's it like working in this environment?
24/7 on call for million-dollar training runs. You get woken up because a single GPU in rack 1847 is running 2 degrees hotter than expected. The stress is unreal. I've seen engineers have panic attacks during system upgrades because one mistake could waste months of work and millions of dollars.
The psychological pressure is insane. Every decision you make affects billion-dollar experiments. Deploy the wrong kernel driver, and you've just set back AGI research by 6 months. I've developed performance anxiety about performance optimization.
The scale makes everything existential. You're not just building servers, you're constructing the computational substrate for artificial intelligence. Every design decision might affect the future of human civilization. No pressure.
What about the environmental impact? Are we burning the planet to train chatbots?
The carbon footprint is staggering. Training GPT-3 emitted as much CO2 as 126 cars driving for a year. GPT-4 was probably 10x worse. We're accelerating climate change to build systems that can write poetry about climate change. The irony is suffocating.
And the waste heat is massive. We're dumping megawatts of heat into the atmosphere. Some data centers are trying to use the waste heat to warm nearby buildings, but we're basically building computational furnaces that might achieve consciousness.
The resource consumption is unsustainable. We're mining rare earth elements, manufacturing specialized chips, building custom cooling systems, all for models that might be obsolete in 6 months. It's planned obsolescence on a geological scale.
What keeps you up at night about AI infrastructure?
Single points of failure in critical systems. One misconfigured load balancer could crash the entire training job. One power outage could set back research by months. We're building increasingly fragile systems that have to work perfectly all the time.
The complexity is becoming unmanageable. We have millions of lines of infrastructure code, thousands of microservices, distributed systems that nobody fully understands. We're approaching the limits of human cognitive capacity to manage these systems.
That we're building computational infrastructure more complex than civilization itself to create artificial minds we don't understand. We're constructing digital gods using mortal engineering and hoping they don't notice our mistakes.
Any advice for engineers entering AI infrastructure?
Learn distributed systems, understand hardware limitations, prepare for scale you can't imagine. Start with small clusters and work your way up to city-sized data centers. Also, invest in good coffee. You'll be debugging at 3 a.m. more than you sleep.
Master the art of fault tolerance. Everything will fail constantly. Build systems that can recover from any failure mode you can imagine, then prepare for the ones you can't. Also, learn to explain to executives why you need the GDP of a small country to run their chatbot.
Remember, you're building the foundation for artificial intelligence. Every optimization, every design decision, every line of code affects the future of human-AI interaction. Build with responsibility because the stakes are civilization level.
This has been Engineer Panic. We've learned that AI infrastructure consumes more resources than small countries, costs more than space programs, and is approaching the physical limits of reality. But hey, at least our trillion-parameter models can generate infinite cat pictures.
Thanks for the reminder that I'm building computational infrastructure for alien minds. Now excuse me while I debug why rack 4729 is consuming 0.1% more power than expected and might bring down the entire training job.
And I need to explain to the board why our electricity bill is higher than most companies' entire revenue. Turns out artificial intelligence is really, really expensive.
Keep building, keep scaling, keep panicking. The future of artificial intelligence depends on engineers who understand that we're not just building computers, we're constructing the substrate for digital consciousness.
This has been Engineer Panic, where AI infrastructure meets physical reality and both have nervous breakdowns. Until next time, remember, your data center is probably fine, but definitely unsustainable.